All right. So, what was the first question? 118? Swapper. All right. Return a list the same as S-list, but with all occurrences of S1 replaced by S2 and all occurrences of S2 replaced by S1. Okay, so we're going through S-list, and anytime we see a match to S1, we are swapping it with S2. Anytime we see a match for S2, we're replacing it with S1. So really what we're doing is we're building a new list, right? So we're constructing a list, and we're either keeping what's already there, or we're situationally, if we see an S1, we're consing on an S2. If we see an S2, we're consing on an S1. And we're going to keep doing that until we're out of coulders, right? Until our S list is finally empty. Does that sound accurate? So we'll define swapper to be a lambda. This guy's going to take multiple parameters, S1, S2, and S-list. Okay, remind me, what's a lambda expression again? Unnamed procedure, right? And we've named it here by using the define statement. All right. So now we want to ask the question if we're dealing with the empty list. If we're dealing with the empty list, we know we're done. And our pattern is to go ahead and return the empty list. That way we can finish our final cons, right? Because we're going to be consing onto the cons, onto the cons, onto the cons, until we finally get our final parameter that's going to be an empty list, which will let all that stuff unroll. So we'll say if null S list, go ahead and return the empty list. Otherwise, just out of curiosity, why is it better to return the empty list here rather than return S list? If we know that S list is the empty list. Why is it faster? Doesn't have to resolve the variable named S list. From our perspective, they're equivalent, right? But if we're thinking about this from a language theory perspective, performance-wise, the empty list, just the value empty list, is faster than saying S list resolve to empty list. All right, so if we're in this else here, that means that we definitely have a car. So now we want to ask the question if the car is equal to the guy we're currently looking at, right? So we'll ask another if the car of S list, and we want to know if this dude is equal to, does it tell us the nature of our list here? Let me check something here real quick. I'm just going to steal this. Does it guarantee us by this definition that S1 and S2, oh, those guys are going to be symbols. So we can use the equal sign for them?
I think in the book it said when they say like S list, it's
Okay. Well, but here's a list containing in there.
Yeah.
But it's a list of 0 symbols. So an S list is a list of symbols or S lists. I was more asking about this, the S1 and S2, whether those guys are guaranteed to be symbols. It looks like they're treating them as symbols, so we can use the equal sign. All right, so if the car of this guy is equal to S1, then I'm going to cons S1, or I'm sorry, cons S2. If it's equal to S1, I need to replace it with S2, right? So therefore, if I find an S1, I'm going to ignore it, and instead I'm going to cons S2 onto whatever's returned by swapper S1, S2, cooter of S list.
Wouldn't you have to make sure that the car of S list isn't the list itself first?
The car of S list isn't a list itself.
Yeah.
Why would
You
I?
have to look, if it's like list X, you have to look inside that list to get the actual.
Oh, so that's going. So you want to operate off the definition where this guy can be a list of lists.
Right.
Okay, I'm fine with that. All right, so if we have a match then, if I'm here, if the car of S list is equal to S1,
Yeah.
okay, then I'm either going to cons this directly onto it, or I actually need to, well, actually, hold on.
You have to check those.
No, I won't, because if S1 is a symbol, if we're guaranteeing S1 and S2 is a symbol, and the car of S list matches that symbol, then we know it's a symbol. We know it's not a list.
If the symbol that we're looking for is already part of a nested list, it would return the list that contains the symbol. And what we're saying is we need to still look inside that list to.
Right, but so this if statement just says if the first element is the symbol.
Yeah.
Then we can go ahead and do it. Then you want to say if the first element is a list, we need to go ahead and do swapper on that list.
Right.
And cons that on. Yeah, so we're okay with what we have initially. So we're going to cons S2 onto swapper S1, S2, cooter of S list. That's if the first element we're looking at is indeed S1, the symbol S1. All right. Otherwise, if it's not the symbol S1, it might be the symbol S2. So let's do another if. If equal car of S list is S2, then we'll go ahead and cons S1 onto the swapper of S1, S2, cooter, S list, like that. So now we've done the swaps when we have symbols at the top level, right? All right, so now you want to say, well, what if, so if we're in this else here, that means we know the car is not S1. We know the car is not S2. So now the car is something else. But that something else might be a list that contains an S1 or an S2, right? So I think that you probably could have interpreted this question a couple of different ways. You could have gone this route and this would be okay. This is certainly a more complex route. Or you could have assumed that your S list, you didn't, I mean, did any of the examples give you that you had to go in deeper?
Yeah.
Oh, it did. Yeah. So we can't assume that. It's a list that can potentially contain other lists. All right. So if we're in this else right here, we know that the car is not S1. We know the car is not S2, but the car might be a symbol. If the car is just a symbol, we can just cons it, right? So else if symbol car S list. So if the first element of S list is not a list, that's what that says. If it's just a symbol, then we're going to go ahead and cons car of S list onto swapper S1, S2, cooter. S list like that. So first element's not S1, it's not S2, but it is a symbol. Just keep the symbol, cons it onto swapper for the rest of the list. Otherwise, if we're in this else, that means the first element is a list. And if the first element is a list, we need to call swapper on that list. So what are we going to do? We're going to cons swapper S1, S2 on the car of S list onto swapper S1, S2 cooter of S list. Something along those lines? All right, so walking through this, if we have run out of crap to check, return the empty list. That becomes the final case for any of these conses. So this cons, this cons, this cons, this cons. At the end of the day is always going to expect the very last parameter to be a list. So we'll go ahead and return an empty list just to complete the recursion. Okay, so when we're out of crap to check, this ends the recursive calls right there. Otherwise, we're going to check to see if the first element is the same thing as S1. If it is the same thing as S1, we're going to go ahead and ignore it and replace it with S2, consing S2 onto whatever swapper returns for the rest of the list. Otherwise, if the first element of S-list is S2, we'll ignore it, we'll cons on, so now we're swapping the S2 for S1, so we'll cons S1 onto whatever swapper returns for the rest of the list. Otherwise, we know it doesn't match S1 or S2, so now it's one of two things. It's either a symbol, but some other symbol other than S1 and S2, or it's a list. So we'll ask if it's a symbol, then go ahead and just keep that symbol, whatever it was. We know it's not S1, we know it's not S2, it's something else. Whatever it was, we'll keep it. So we'll cons that symbol onto whatever swapper returns for the rest. Else, so right here, this is when the car of the list is a list. And therefore, we might need to do the swapper stuff for that list. So we'll go ahead and cons whatever's returned by swapper, passing it S1, S2, and the first element of the list, which is a list, onto whatever's returned by swapper, passing it S1, S2, and the rest of the list. That make sense? Now, actually, let me test something here real quick. Just run that. Yeah, that'll work. I wanted to make sure that if you cons the list onto another list, it didn't merge the list together into a single list ABC. I wanted to make sure the first element was still going to be a list. So we should be able to test this with a couple of these guys. We got to fix our... Oh, equal sign is only for comparing numbers. So I think we need to do EQ like that. All right, so the first A became a D, then a B. Oh, design programs. CA. Yep, so worked for that one. And oh, thank you. All right, worked for that one. Looks good. DA, empty, CA. YX list ZY. Looks right. All right, so there is that one. Questions about that? All right. Next question. Ooh, 2-star. Varies. Do we have 3? What? 118, 119, 120? Okay. List set takes a list, a number, and X returns a list like LST, except that the nth element using zero-based indexing is an X. So we are replacing whatever's at bucket N with whatever the value was at X. So we're going to keep going through it, consing, except when we finally get to the bucket whatever, we're not going to cons the element that's on there. Instead, we're going to cons X on there onto the return of the decoder of the rest of it. Why is that 2-star? Yeah, so what we're going to do is we're going to use this N as a counter. And we're just going to count down from the current value of it down to 0. And once we hit 0 on it, so 2, 1, 0, that means we're at the correct bucket. So once it's equal to 0, we're going to cons a replacement on. Otherwise, we'll just keep going until it's empty. So this guy's called list set. So list set is going to be a lambda that takes a list, a number, and an X with the right parameters. Okay. So then we're going to ask the question if null LST, go ahead and return the empty list. So that's our kind of our pattern stopping case. All right. So if we still have stuff in our list, then we're going to ask the question if equal n0. There's also a predicate you can use for checking to see if something is 0, and that is the 0 predicate, like that. I think I mentioned the word predicate in here before, right? Predicate is a function that returns true or false. Typically takes one parameter. Function taking one parameter that returns true or false, just a fancy name for that. All right, so we have and typically in scheme, predicates have a little question mark at the end of it. More of a naming convention, that's just a thing. All right, but we'll stick with the equal thing. So equal n0. If that's the case, then we'll go ahead and cons X onto list set minus n1. We need to pass that the new list to decoder of list minus n1.
Wouldn't you still want to add X onto the list instead of just returning onto the list that you took in as well? Or are you saying, do you know what my question is?
You're asking, do I want to have this be the list containing X?
Yeah, that's what I'm asking.
If we have the empty list. So this would be error checking, right? If the value was 0. So how would it work if you had the empty list and you said put it bucket 0 and A? In that particular case, if the list is empty and n was 0, then you should return the list containing X. So that really would be error checking. Otherwise, I mean, I think what you're suggesting, well, no, because that would only, I think what you were suggesting would only work if we're at the end of the list.
Okay.
Because otherwise, this is where I'm doing my swap here, right? In the cons here. But technically, in a error case, if I did have the empty list and that happened to be the exact same time that n was also equal to 0, then I would want to return the list version of X. So rather than just blanketly, so the possibility is if I'm right here, I haven't necessarily put my X in yet. Therefore, so really I should ask another question here. I should say if equals n0, 0 here.
Then you would want to.
That's if it is the empty list. Then I'd want to return the list containing X. Else, I want to do all this stuff. So this effectively says, if I'm looking at the empty list and I'm currently at an n as 0, this actually is the place I should be putting my answer. That it should be.
That's kind of what I was wondering.
Yeah.
Where would you be?
So this guy right here happens if we're dealing with the empty list and we are dealing with actually we need to go back here because then the opposite would be that. So if we're dealing with the empty list and n is equal to 0, I should return the list containing X. That's if we have the empty list and we're trying to put at bucket 0 something. Otherwise, go ahead and return the empty list. Presumably, we've already placed our X. All right, so all that only happens in the event that we have the empty list and this is also, we're at an n as 0. Otherwise, if n is 0, if n is 0 and we aren't dealing with the empty list, then go ahead and cons an X onto, let me make sure I'm ending at the right place here. I am. So if n is equal to 0 and we're not dealing with the empty list, then cons the current value of X onto whatever list set returns for the rest of my list, a value that's 1 smaller than n and the X. Otherwise, if n is not equal to 0, then what am I going to do? I'm going to cons the car of LST onto the list set of the coder of LST, passing it minus n1 and x. So if this is the guy I'm supposed to replace it. If it's not the guy I'm supposed to replace, keep what was already there, and then call list set again on the rest. All right, so let's test this guy. Oh. Okay, that looks right for that one. List ref gives us the value that you replaced. So they're just proving that it was in the right place. So list ref is the antithesis of list set. So list ref says, give me the value at a particular bucket in a list. After we've set bucket 3 in that list to 1, 5, 10, getting bucket 3 should give us the 1, 5, 10. That's just because the output is kind of, lots of crap. This will show us the, although you know what? It should be pretty easy to view that. So we'll just view it directly. All right, so 0, 1, 2, 3. So the last element here, D, should actually be the list 1, 5, 10. So there's our list 1, 5, 10. Make sense? All right, questions on that one. And just to test that special case, because they didn't actually have this special case in here, why don't we go ahead and we'll say, here's the empty list. Go ahead and replace bucket 0 with 1, 5, 10. So that gives us the list containing the list 1, 5, 10. Go ahead.
So can you just walk through that whole thing and explain
I cannot. I actually blacked out when I was doing this. I have no idea what this does. All right, you want me to go through just step by step what this guy does?
Yeah.
Okay. So, well, first of all, you understand what we're trying to do, right? Okay. So this first part here says if we're looking at the empty list. So this is our special case here, the thing we just showed here. What if we were to call our function passing it the empty list and saying I want to put at bucket 0 another value? That's what this little thing here does. It says if we're looking at the empty list and n is currently 0, go ahead and make a list out of x. So this is that special case where we have the empty list and we haven't already placed our x. All right, so call that the special case there. Otherwise, if we're dealing with the empty list, go ahead and return the empty list. That's our typical pattern we've had. All right, so we're good up to that point? So that's the end of our recursion. Otherwise, so this, if we're down here, that means we're not dealing with an empty list. We got stuff, okay? If n is currently 0, and the reason we're doing this is n starts off at some number. So like in one of our examples, it was 3. We're actually counting that number down. 3, then 2, then 1, then 0. And when it's 0, we know we've walked in to bucket 3, okay? So if n is 0, that means that we are currently at the bucket in our original list where we are replacing with our x. Therefore, we're going to go ahead and cons the x onto list set on the rest of our list. 1 smaller than n used to be, so it'll go to -1. No big deal since we're checking for it being exactly equal to 0. And x. We also don't even need the x anymore, but it's part of the syntax. This guy requires 3 parameters. All right, so if this is the guy I'm supposed to replace, go ahead and cons my replacement value, effectively ignoring what was at the car, along with whatever's returned by list set for everything else. Otherwise, if this was not the guy I'm supposed to replace, go ahead and cons the first element just as is. We're not replacing anything, along with onto list set for everything else. Questions about that? All right, so everybody's good with that one? All right. And then 120, count occurrences. Was this one hard? What was the hard one? So far, these all seem trivial. Actually, the first one wasn't too trivial. Depends how anal you want to be about this, but this one probably should have been a 2-star. This one probably should have been a 1-star. So it was an even trade. 120. Count occurrences, passing in a symbol and an S list, and this guy should return the number of occurrences of S in the S list. Okay. I don't want to have to spell occurrences, so we're going to steal.
No, that was a pain. Good programming this one.
Define count occurrences to be lambda S and S list. 2 parameters, S list. Like that. Okay, so our job is to count the number of elements. So we are counting. So we're introducing a new pattern here. Up to this point, our pattern has been building lists, okay? Which in our mind, based on where we've come from in all of our classes with Java and stuff like that, we should probably kind of think about it as like building strings. It's similar enough to that, right? Okay, but now this is a new pattern. Now we're not building an output. Instead, we're accumulating an output, counting some stuff. All right, so if S list is empty, if I'm out of stuff, what am I going to return? 0. I'm going to boil down to nothing because I've been adding stuff together leading up to this point. And when I'm finally done, I'm going to add a 0 to it. And anything plus 0 is what? Whatever you used to have is the anything. Okay, 0 is not going to impact it, so that's our stop case. So if I'm out of places to check, go ahead and return a 0. Otherwise, I have something to check. If the first element is the thing I'm looking for, is S, that must mean it's I'm going to count 1, right? Okay, so if equal S car S list, those guys are equal to each other, I'm going to add 1 onto count occurrences S could of S list. Okay. Now we get back to the same pattern Corey pointed out from the first one, that we need to ask that question: are we dealing with a list next, or are we dealing with? Actually, it wasn't Corey. It was, are we dealing with a list, or are we dealing with a symbol? So, if I found a match, add 1. Otherwise, if symbol car S list, the first element is a symbol, and I know it didn't match the symbol I was looking for, then what am I going to return? Now, there's a couple of ways you can go about this. If you want it to look mathy, one thing you could do if you want to see that pattern is you can go ahead and say +0 onto count occurrences of S cooter S list. Now, that's actually redundant, right? 0 plus anything is going to be anything, so really we could have just returned count occurrences for S on this. So I'll show you that alternative in a second, but this really shows the pattern we're after here. I found a match, so add 1. I didn't find a match, so add 0. Make sense? Even though we know mathematically adding 0 is a waste of time.
Could you use the predicate if list, like list question mark?
You can, but it's the same thing. So this is saying if the first element is a symbol, do this, else it must be a list. You want to say if it's a list, do this, else it must be a symbol. That's same question, right? Although I did look, I don't care if you use list, that's fine. I didn't think I saw them use the list predicate in the book up to that point. It's not a big deal. It's fine. It's not like a cheat code or something. You're asking the same question, but I wanted to make sure I solved them using the stuff that the book had already introduced. What he's referencing is there is a predicate called that returns true if the parameter you give it is a list. So it'll return a true for that. And it'll return a false for that. Make sense? So it allows you to detect whether something is a list or not. For right now, we know that the thing we're working with is either going to be a symbol or a list. So we'll ask if it's a symbol. If it's not, it must be a list. All right, so if it's not a symbol, must be a list. So if it's a list, I actually need to count occurrences on that list and add to that count occurrences on the rest. So I'm going to sum whatever count occurrences on car, count occurrences of S on car S list to count occurrences of S on cooter S list. Like that. Make sense? And if you want to shorten this just a little bit, understand that this +0 thing is inefficient. We didn't really need to do any math there, so we could have just done that. The first element is a symbol, but it's not the symbol we're looking for. Just go ahead and call count occurrences on everything else. But some of you maybe would prefer to see it like that, because it kind of exaggerates the pattern a little bit. That's okay. Be a little inefficient if it helps you see the pattern a bit. Questions on this one? Go ahead.
So, like, since we're trying to like count like how many times like S is like showing up, I guess like for the +1, like I know that's like adding, like saying, oh, we counted 1, but like how is it? So like I guess like in Java or whatever, we always have just done like we set a variable count. So like, is it like is that a built-in thing in here where it's like saying like, oh, +1 is automatically
No, so this is based on the recursion. So if I find a match, I'm starting to add some stuff. I'm going to say, well, okay, so I'm going to add 1 plus whatever that function returns for everything else. Let's say the next time through it returns 1 again, plus whatever it returns for everything else. And let's keep it short because I'm running out of hands. So let's say we're out of things now. Now it's 1 plus 1, which is 2. I found 2 occurrences. So we didn't return an individual value. We returned a value plus the result of a function call. And so those things end up accumulating. So rather than storing it in a variable, we stored it in what will end up being the stack, which is how recursion is implemented. And we'll end up doing that. So when we actually start writing our language in here, we will at some point implement recursion. And the way recursion is implemented is as a stack. So we're going to say +1, 2, and then this guy's going to be put on hold because we have to make another call to that function. So we have to push the current value, the current function call onto the stack because we're not done with it. We can't resolve it yet because we're still waiting on an answer from that recursive call. And then we keep shoving stuff on the stack, and we've seen this evidence before when we did recursion in Java. Usually the first day I introduce recursion, I usually create an infinite recursion where Java eventually errors out and says stack overflow exception. So it uses the word stack, saying you've made too many recursive calls and your recursion needs to end and yours doesn't. So, so that's equivalent to the infinite loop in recursion. But infinite loops in recursion are actually quite bad because you will literally run out of memory. So that's why working with something like with a virtual machine like Java or a language that has a check for stack size, a lot of times our languages that support recursion, they have a maximum stack size that you can decide to expand if you need to, because you could probably come up with an example in Java where you get a stack overflow exception, but your code is accurate. You just happen to be making so many recursive calls that you did actually run out of stack space, but not because of poorly written code, just because you made a lot of recursive calls. So with that in mind, you might actually, when you run that program, you might want to pass the Java virtual machine the flag to increase the stack size. Because your code might work. It just needs a bigger stack than the default. Because the default stack is actually relatively small in the big scheme of things so that you don't eat up all your computer's memory when the virtual machine launches. Because the Java virtual machine is running, and it's a piece of software. So if you say I want a stack size, let's say the default stack size is, 8 megabytes. I don't know what the default is, but let's just say it's 8. Okay, and all of a sudden you say I want it to be 3 gigabytes. Well, that means when that program launches, it's going to grab 3 gigabytes of real memory that other programs now don't have access to. Because it's going to have to reserve all that resource because now that program needs it. Does that make sense? So that's why they pick a relatively small number, because most of the time it's fine. Most of the time when you're making a recursive call, you're only calling it, a dozen times or something like that. Not a ridiculous number of times. Okay. Oh, technically I did not test this one, right? We should test it. It'd be so nice if these single quotes came through as single quotes. Is this one supposed to give me a 3? That one gives me a 3. Oh, that's disappointing. Okay. And this last one gives me a 0. Oh, I can just use the same thing from above. We'll just search for a W in this. There's my 0. All right, so we've exhaustively checked that. It works perfectly for every input you can ever give it. All right, let me copy this, throw this up on Slack.
Are you giving us a Bible verse this week or no?
Yeah, it's already up.
I didn't see it.
I put it up maybe an hour ago or 2 hours ago. I would have put it up. I was homesick yesterday, so I didn't get it up yesterday. It's right at the beginning of the semester. It's because all you people, you bring back all the diseases from wherever home is. I almost actually avoided it this time because most of, let's see, is Lisp a language on here? Oh, it is. I want a schema language. Look at that. Because I actually got sick Saturday, Sunday, and I was like half better Monday. I just had an 8 o'clock class, and I wasn't prepared at that point to be alive. So almost avoided missing any classes. All right, so let's see. So we need to probably go a little more difficult for this next one. Ooh, 2 stars. Product of those two. Oh, man, that one sucks. So let's do. Let's do 1, 2, 1 and 1, 2, 2. Sound good? I'll put it up. Like, you want to do 1, 2, 3 as well? Just those two? Well, how long did we spend in this last assignment? Like 45 minutes, an hour? 6 hours? Took you 6 hours to do that?
I got lost in the second one. I overthought it.
Anybody spend more than 6 hours? Anybody who should have spent more than 6 hours but instead turned in incomplete work? Remember, I did tell you the first day of class that this is going to be hard, right? Like, that's why I get so much enjoyment out of it. All right, I will see everybody on... What day is today? Wednesday, Friday.